Welcome to the deep dive. If you're tuning in, chances are you're fascinated by mathematical structures, maybe even sequences from the OEIS, the Online Encyclopedia of Integer Sequences. You might have seen things like as000248, counting idempotent maps on a set functions, where doing them twice is, well, the same as doing them once.
That idempotent property, FFX,
Yeah.
it's remarkably simple, isn't it? Like multiplying by 1 or projecting something. Do it again, nothing changes.
Exactly. But today we're taking a different path. We're not just counting those set mappings. We've got these two sources you provided, and our mission is to unpack how idempotence shows up in, frankly, much more advanced areas.
That's the plan. We'll be looking at discrete integrable systems in one paper and then operators on Banach spaces in the other. Functional analysis territory.
Right, completely different fields. And guiding us through this is our expert guest, a Fields Medal-winning mathematician. That's for joining us.
It's my pleasure. It's genuinely interesting to see how this one idea, idempotence, weaves through such different mathematical fabrics. It provides structure in really unexpected ways sometimes. It really does. So, okay, let's dive into that first source. The title is Idempotent-Compatible Maps and Discrete Integrable Systems. What are we looking at here? Not just functions on single elements, right?
No, not quite. Here, the focus is on transformations, let's call them Q, that take an ordered pair of elements, say x, y, from a set x cross x and map it to a new pair, UA.
Okay.
So Q maps x, y to UV, and U and V are calculated from x and y using some functions, say fxy and gxy.
A map from a pair to a pair.
Yeah.
And where does this fit in? Why study these?
Well, they're fundamental in the theory of discrete integrable systems. Think about a grid like the standard integer grid or maybe something more complex like the triangular QA arrow they mentioned.
Right. You can imagine x and y as values at adjacent points on this grid. The map Q then describes how these values transform together. It often governs the evolution, or maybe the consistency, of some system defined across this whole lattice.
Got it. So they link points on a grid. Now, the paper talks about a property called 3D compatible. That sounds more involved.
It is. And it's often where the integrability part comes into play.
Yeah.
3D compatibility is about how these maps behave when you think about them acting on three factors, like in x cross x cross x. Imagine a cube.
Yeah.
A map Q might act on the xy plane or the x plane or your
Yep.
y's. So transforming two coordinates at a time. The 3D compatibility property means that if you combine these maps acting on different pairs of factors, they have to satisfy certain consistency conditions.
Consistency, you mean like it doesn't matter which face of the cube you sort of process first?
Yeah. Exactly that kind of idea. The paper shows an equation. It's actually related to the famous Yang-Baxter equation that spells this out. It involves the map Q and its inverse core acting on different pairs of factors, like first and third, second and third. The equation basically says doing these transformations in one specific order gives the same result as doing them in a different related order. It's a right euro circle core equals core euro circle euro, that kind of structure.
Yeah, okay. That looks complicated, but the idea is consistency across dimensions.
Precisely. And that consistency is a really strong sign that the system governed by these maps is integrable, meaning it's likely solvable or has some nice hidden structure.
That makes sense. So this property guarantees things mesh together properly. The paper mentions specific examples, right? QI, QII, QII. Are these just abstract ideas?
No, they're quite concrete. They're derived from specific types of rational functions of x and y. The paper mentions multiplicative or additive separable forms. Their exact structure is what grants them this 3D compatibility.
I see.
And there's a neat detail. The definition they give for QI actually means it's not invertible, which is interesting because the general 3D compatibility equation I mentioned uses Q.
Oh, right. So the property can apply even if not all maps involved are strictly invertible?
It seems so, yes. It broadens the applicability.
What about these complementary maps? They use a hat symbol, hat Q.
Ah, yes. The complementary map, hat Q, is basically defined by swapping the roles of inputs and outputs in the original map Q, kind of like running it in reverse, conceptually.
Okay.
And the remarkable finding for these specific maps, QI33, is that their complementary maps, hat QI3, turn out to be equivalent to the original maps themselves.
Really? So the map and its sort of opposite are essentially the same thing structurally?
For these particular examples, yes. And importantly, it means these complementary maps are also idempotent and 3D compatible.
Which isn't necessarily true for just any map, I suppose.
Not at all. It's special to these integrable structures.
How does this link back to the grids and the discrete systems you mentioned earlier?
This is where it connects beautifully. These compatible maps directly generate different systems equations relating values at different points on those lattices.
Right.
Take QI on that QA Euro lattice, which has black and white triangular cells.
Right.
Applying QI leads to a system of equations. And the paper shows that one specific version, equation 21 using a variable phi, is actually a linearization of the discrete Burger's equation.
The Burger's equation. That's a big deal in fluid dynamics and things, right? For shock waves.
Exactly, a well-known model.
Mm.
And this linearization arises naturally from the QI map, specifically living on the black triangles of that lattice.
Okay, so QI governs the black triangles. Let me guess the complementary map, hat QI.
You got it. The system derived from HAQ-UI describes related dynamics, but on the white triangles of the same lattice.
That's really elegant. The map and its complement cover the whole structure, each taking half.
Precisely. They provide the dynamics for the other half of the lattice. Together, they describe the full discrete system.
And they showed this with initial value problems too, right? With those blue and red circles in figure 4.
Yes. That figure illustrates how setting values on some points, the blue ones, lets you propagate the solution to the others, the red ones, using these map rules. The 3D compatibility ensures it all works out consistently, no matter how you spread across the grid.
It's a really sophisticated way that idempotence, hidden inside this compatibility property, dictates the structure of these complex grid dynamics. Amazing.
It really is.
Okay, let's switch gears completely. The second source. This feels like entering a different mathematical world, functional analysis, operators, infinite dimensions, Banach spaces.
It is quite a shift, but we still find idempotent at the heart of it. Here, it refers to a type of operator, a bounded linear operator, usually called P, acting on a Banach space X.
And a Banach space is like an infinite dimensional vector space, but with notions of distance and limits that work well. Calculus in infinite dimensions.
That's a good way to think about it, yes. Bx is the collection of all bounded linear operators on X linear transformations that don't blow vectors up infinitely.
Yeah.
And P is idempotent if P squared equals P, Px, Px.
So like those projection operators we mentioned earlier. Project onto a subspace, and doing it again keeps you there.
Exactly. Px is the set of all these idempotent projection-like operators on the space X.
And this paper isn't looking at dynamics on the space X, but relationships between these idempotent operators, P themselves.
That's the core idea. They define and study specific relationships on this set, Px. Two key ones are, first, a partial order. PQ if and only if PQ QP equals P.
Which means?
Conceptually, P projects onto a subspace that's inside the subspace. Q projects onto. And crucially, they have to commute. The order of applying them doesn't matter for vectors projected by P.
Okay, order. What's the second one?
Orthogonality. POQ if and only if PQ equals QP equals 0s. This means their images, the subspaces they project onto, only overlap at the zero vector. They project onto completely separate directions, essentially, and again, they must commute.
Right. So we have these idempotent objects, P, and ways to relate them, one containing the other, order, or being totally separate, orthogonality. What's the paper trying to do with these?
The main objective is to figure out what kinds of maps on the set Px itself preserve these relationships. They look at bijective maps 1-to-1 and onto transformations of Px to itself, let's call 1. And they ask if T and Q are related, say POQ. Does PQ have to hold, and vice versa? What maps have this property?
Okay, characterizing the structure of maps that respect the structure of Px. What do they find? Are these maps just anything goes, or are they special?
Oh, they are very special, highly constrained. One really interesting finding first, proposition 1.1, a bijective map on Px preserves orthogonality in both directions, if and only if it preserves the partial order in both directions.
Wait, preserving perpendicularity is the same as preserving the subset relationship for these maps. That seems unexpected.
It is quite surprising. It links these two geometrically different seeming relations under these transformations.
Okay, that's a cool link. But what about the maps themselves? What do they actually look like?
This is where the main theorems come in. Theorems 1.2, 1.3. For infinite dimensional Banach spaces, these bijective maps preserving orthogonality or commutativity, which is closely related, almost always have a very specific algebraic form. They're typically similarity transformations.
Similarity transformation. What does that mean here?
It means the map takes an idempotent P and sends it to TP2, where T is some invertible bounded linear operator on the space X.
Ah, okay. TPT inverse. That form shows up a lot in operator theory, doesn't it? Like changing basis.
Exactly. It's essentially like viewing the operator P after a change of coordinates defined by T, and then changing back via T. It preserves the fundamental algebraic nature of P. So these structure-preserving maps are, in a sense, quite tame. They're just these conjugations by T.
So mostly just change of basis. Are there any catches?
A few nuances. If the Banach space is complex, T could be linear or conjugate linear. Also, sometimes the map involves the adjoint operator P. So P might map to T, P, T. This usually involves T being an operator mapping from the dual space X to X, and often requires the space X to be reflexive for it all to hang together.
Okay, so TP T inverse, or maybe P star T inverse. What about that ortho permutation thing mentioned for commutativity?
Right, that's another possibility, theorem 1.3. For maps preserving commutativity, the structure can be slightly more complex. The map might be composed with another transformation, which can swap P with its complement I minus P, where I is the identity.
So it could map P to T PT or potentially to T IP?
Essentially, yes. IP plus 1P IP, where he's like a switch, 0 or 1, depending on P. So it adds another layer beyond just the pure similarity.
Okay, so mostly similarity transformations, maybe involving adjoints, maybe this ortho permutation twist. Does it matter if the idempotents have a specific finite rank, like rank n?
Good question. They address that too, theorems 1.8, 1.9. They look at the subset P and X idempotence projecting onto an n-dimensional subspace. The results are broadly similar. Projective maps preserving the relations on P and X are, again, typically of the form TPT or TP2.
So the finite rank doesn't drastically change the form of the preserving maps?
Not fundamentally, no. The proofs might use slightly different techniques, like relating things via adjacency when the rank of P minus Q is small, but the endpoint is structurally similar.
And then they use all this to say something about maps on the entire algebra BX.
Yes, that's a nice application, theorem 4.1. They leverage these results about idempotence to characterize biseparating maps on the whole algebra BX. A biseparating map is one that preserves zero products. A times B is 0 if and only if A times B is 0.
I see.
It turns out that understanding how these maps act just on the idempotence within BX is crucial for understanding their structure overall. Again, they often relate back to similarity transformations.
Okay, wow. Let's try and synthesize this. We started with idempotence, like fx. Source 1 showed us idempotent-compatible maps structuring dynamics on grids, connecting to integrable systems, even the discrete Burger's equation.
Right. In that context, idempotence, through this lens of compatibility, was a property of the map itself. It governed how things change or relate consistently across a discrete spacetime.
Then source 2 took us to functional analysis. Idempotent operators, P or P, acting like projections, and maps between these operators that preserve their relationships, order, orthogonality, had to have this rigid similarity-based structure, TPTU.
Exactly. There, idempotence defined the objects of study the operators P. And the property ended up constraining the types of transformations allowed between these objects if you want to preserve their fundamental relations. It dictates the structure of the maps on the space of idempotence.
So the same simple algebraic role, PAP, manifests completely differently. In one case, it enables consistent evolution on a grid. In the other, it dictates the form of maps between operators.
It's a fantastic example of how a single basic algebraic property can lead to profound and diverse structural consequences depending on the mathematical universe you're exploring.
That's a great summary. Thank you so much for walking us through these. They were definitely deep dives into complex territory.
It was my pleasure. Always fascinating to trace these conceptual threads.
So for everyone listening, we saw idempotence move from maybe a simple counting problem on sets or a basic projection idea into the backbone of discrete integrable systems via compatibility, and then into defining the very nature of structure-preserving maps between operators on infinite dimensional spaces. It makes you wonder, doesn't it? How can one elementary property, p squared equals p, lead to such different kinds of mathematical depth? Structure for dynamics in one case, structure for transformations in another. What does that say about the power locked inside simple axioms?
A profound question indeed.
If any of this sparked your interest, maybe exploring discrete integrable systems or digging into functional analysis and operator theory could be a next step. The papers themselves or introductory texts might be a place to start. That's all the time we have for this deep dive. Join us next time as we tackle another fascinating topic from the source materials you provide.